think it's based on functional neuroanatomy. The basal ganglia are composed of subcortical nuclei that are interconnected with the cerebral cortex, brainstem, and the thalamus. Which of the following is true? Before going into the right answer, let me tell you the functional neuroanatomy of basal ganglia. And before going into the functional neuroanatomy, let us understand the gross anatomy. Basal ganglia is composed of two very important subcortical nuclei. One is the caudate nucleus, and second one, of course, is going to be the lentiform nucleus. Lentiform nucleus is further subdivided into putamen and the globus pallidus. Globus pallidus is further subdivided into globus pallidus externus and globus pallidus internus. And we know the fibers of internal capsule are the ones that are going to pass between the caudate and the lentiform nucleus. But functionally, things work a little different. I can combine caudate and putamen together in a single structure called as striatum or neostriatum. And striatum is the one that's going to serve as input nucleus to the basal ganglia. Which means whatever input that comes into the basal ganglia has to come through the striatum. That's why it's called input nucleus. And globus pallidus, as we know, can be divided into globus pallidus externus and globus pallidus internus. In this globus pallidus internus is considered to be extrinsic nucleus of the basal ganglia because it's the one that's going to give output from the basal ganglia to other structures, especially structures like thalamus, where the impulse will travel back into the cortex. So the output from the basal ganglia is going to happen through globus pallidus internus, and the input into the basal ganglia is going to happen through the striatum, that is caudate and putamen together. And what about globus pallidus externus? Globus pallidus externus is something that's going to connect the input and the output nucleus. So that's why globus pallidus externus is the intrinsic nucleus of the basal ganglia. And we have two different pathways that exist within the basal ganglia. One is called as the direct pathway and the second one is called as the indirect pathway. And we'll discuss about that in a while. And these two pathways are modulated by two other pathways. One is called as dopaminergic modulation and second one is called as cholinergic modulation. First, let us look at the simple direct pathway first. What happens in the direct pathway? So you have cortex. Cortex is going to give input to the basal ganglia, and the input has to happen into the striatum first, as we all know. That's why these fibers are rightly called as corticostrial fibers or corticostrial neurons. And the major neurotransmitter that they're going to release is going to be glutamate, which is an excitatory neurotransmitter. And once the input comes into the striatum, the strial fibers will be then activated and they're going to give further stimulus to the globus pallidus internus directly. And these fibers are called as striopallidal fibers. And remember, whatever the fibers are from within the basal ganglia doesn't matter. They're going to secrete only one neurotransmitter that is called as GABA. So basal ganglia fibers are GABAergic in nature. They are inhibitory. So whatever may be the fibers, it could be coming from the striatum, it could be coming from globus pallidus externus, or it could be coming from globus pallidus internus. Doesn't matter. They're going to release GABA only. They are GABAergic fibers. And from the globus pallidus internus, you're going to have another set of fibers that are going to reach the thalamus. And we know thalamus is a relay center. So what are the information that goes into the cortex? Majority of them has to pass through the thalamus and then only they can go into the cortex. So thalamus is a relay center. So these fibers will be pallidothalamic fibers because we know the fibers that are coming as output from the basal ganglia has to come from globus pallidus internus only because it's the output nucleus. And once again, these fibers are going to release GABA only because I told you whatever fibers that are present in the basal ganglia are going to be GABAergic, as simple as that. And through the thalamus, the information is going to go back into the cortex. And these fibers once again will be going to release glutamine only. And rightly, these fibers will be called as thalamocortical fibers. This is what we call as the direct pathway. So where the impulse comes from the cortex, goes through the basal ganglia and then back into the cortex through the thalamus. Simple direct pathway. So what is the function of the direct pathway? It's going to activate the cortex. It's going to activate the cortex for a particular moment. That's what is happening here. So let us understand what's happening. So we know that corticostrial fibers are basically excitated, releasing glutamine. So they're going to increase the activity of the fibers that are present in this striatum, which means the strial fibers are going to have increased activity, which means they're going to release more GABA. They release more GABA. The fibers at the level of globus pallidus internus are going to be inhibited because GABA is an inhibited neurotransmitter, as we know. And this in turn is going to have effect in the form of reduced activity of this pallidothalamic fibers. So which means they are going to release less GABA at the thalamic level. So if they are going to release lesser amount of inhibitory neurotransmitter, that is going to result in increased activity of thalamocortical fibers, which means there will be increased release of glutamate by the thalamocortical fibers. That probably explains why the direct pathway is a kind of pathway that's going to cause cortical activation for a particular moment. And first of all, what is the function of the basal ganglia? Basal ganglia is something that's going to fine-tune your movement. That's the major function. Basal ganglia may contain programs for some specific movements, especially fine movements. And cortex is trying to extract that programs from the basal ganglia. That's what is happening as a whole here. And this is the simple direct pathway. And what about indirect pathway? So once again, let us draw the structures. You're going to have the striatum, which is the input nucleus, and we have the globus pallidus externus, which is intrinsic nucleus of the basal ganglia, and we have the globus pallidus internus, which is the extrinsic nucleus of the basal ganglia, which is also going to be the output nucleus. And then of course we have the thalamus, which is the relay center for the cortex. And in the indirect pathway, we're going to have an additional structure that is called as subthalamic nucleus. That will be involved here. So what's going to happen? As usual, your input is going to come from the cortex predominantly, and these fibers, as we know, they will be called as corticostrial fibers, and they're going to release glutamate as such. And once the input comes into the striatum, the strial neurons are going to get activated by this glutamate and they're going to release GABA. But in the indirect pathway, they're going to end up in globus pallidus externus and not the globus pallidus internus. Of course, they are going to release GABA only because they are GABAergic. And from the globus pallidus externus, you're going to have another set of fibers that are going to enter the subthalamic nucleus. Probably you can call these neurons as pallidosubthalamic neurons. That's correct only. And they are also going to be GABAergic. From the subthalamic nucleus, another set of fibers are going to reach globus pallidus internus and they will be called as subthalamo-pallidal neurons and they're going to be glutaminergic, which means they are going to produce glutamate, which is an excited neurotransmitter. And from the globus pallidus internus, your output fibers fire now and these are called as pallidothalamic fibers and once again they're going to be GABAergic. The pallidothalamic fibers, as we know, are going to be the output fibers which are going to come from the globus pallidus internum only. And from the thalamus, now of course the impulse has to travel back into the cortex. And as we know, these fibers will be called as thalamocortical fibers, which are going to release glutamate at the cortical level. This is the famous indirect pathway. So what is the role of indirect pathway? The role of indirect pathway is to cause cortical inhibition, or probably we can say it's going to reduce the incidence of a particular movement at the cortical level. Okay, so how it does that? Let us understand. So as such, whenever the corticostrial fibers fire, the glutamate is going to activate the striatum, and the strial fibers are going to have increased activity, in the sense they are going to release increased GABA at the level of globus pallidus externus. So increased GABA means the fibers that are coming from the globus pallidus externus will have reduced activity. That is because GABA is going to be an inhibitory neurotransmitter, as we know. And reduced GABA at the level of subthalamic nucleus, because you're going to have reduced activity of the fibers of globus pallidus externus, means you're going to have reduced inhibition at the subthalamic nucleus level, so that there's going to be increased activity of the fibers that are going to originate from the subthalamic nucleus. So they're going to release increased glutamate at the globus pallidus internus level. If you have increased activity of neurons at the globus pallidus internus level, means you're going to have increased release of GABA at the thalamic level. So which means thalamus is going to have reduced activity. So which means the thalamocortical fibers now are going to have reduced activity. So there's going to be reduced release of glutamate at the cortical level. So that is the reason the cortical activation will be reduced, or it can be inhibited with the help of indirect pathway. And why these two pathways exist? Because you need a kind of a fine balance between cortical activation and cortical inhibition. So that's what these two pathways exactly do. So now I think you would have understood what is direct pathway and what is indirect pathway. Now it's time to understand what are the different modulators of this direct pathway and indirect pathway. The most important modulator is the dopamine. So where the dopamine comes from? Dopamine comes from midbrain. And we have a very important area in the midbrain which will be black in color. That's called as substantia nigra pars compacta. Why it's called nigra? Because in your gross anatomical sections, it might appear black because of the presence of amine, that is dopamine there, because these neurons are dopaminergic. And we all know the input has to happen through the striatum. And that is why these neurons are rightly called as nigrostrial neurons. That's why it's called as nigrostrial pathway. So what are the function of nigrostrial neurons? They are going to release dopamine at the level of striatum, which is going to have a kind of modulatory effect at the level of striatum on the striopallidal neurons. So when it comes to direct pathway, the neurons of the direct pathway at the level of striatum has a type of receptor called D1 receptor, and the neurons that are involved in the indirect pathway are going to have dopamine receptors in the form of D2 receptors. So when dopamine acts on the direct pathway on the D1 receptors, it's going to result in activation, because we know D1 receptors are activating receptors. So when dopamine acts on the direct pathway, which is already an activating pathway of the cortex, you're going to result in more activation of the cortex. On the other hand, when dopamine acts on the D2 receptors, we know that D2 receptors are inactivating receptors, which means you're going to have inhibition of the indirect pathway as a whole. So we know indirect pathway is going to cause cortical inhibition, and inhibition of the indirect pathway is also going to result in cortical activation only. As you can see, whether it's direct pathway or indirect pathway, action of dopamine on either of these pathways is going to result in cortical activation only. And this explains what happens in patients with idiopathic Parkinson's disease. In the sense, you're going to have a degeneration of nigrostrial neurons in this disease, and there's going to be reduced amounts of dopamine in the striatum because of degeneration of nigrostrial neurons. And reduced dopamine means there's going to be reduced cortical activation as a whole, and this is the reason for the characteristic symptoms that happen in Parkinson's disease, like bradykinesia, or we can call it as akinesia in extreme situation. That's why Parkinson's disease is another example of akinetic rigid syndrome. And there is another modulating substance that is going to modulate the effects of direct and indirect pathway, and that's going to happen within the striatum, which means these neurons are intrinsic to the striatum, and these are cholinergic neurons, and precisely we can call it as cholinergic interneurons that are present within the striatum, and they're going to release acetylcholine. And what is the role of acetylcholine? Acetylcholine is going to stimulate the direct pathway neurons, and they're going to stimulate the neurons of the indirect pathway as well, which means the role of acetylcholine is to potentiate both the direct pathway as well as indirect pathway. So if it's going to act on direct pathway, it's going to result in more activation of the cortex. If it's going to act on the indirect pathway, it's going to result in more inhibition of the cortex. That's what acetylcholine does. In general, there should be a balance between dopamine and acetylcholine in the striatum. If this balance is disrupted, you can result in variety of disorders. For example, take idiopathic Parkinson disease. We are going to have reduced dopamine at the level of the striatum, even though the absolute amounts of acetylcholine does not increase, but there will be a relative excess of acetylcholine here. And this imbalance between dopamine and acetylcholine is probably thought to be one of the main reasons for symptoms like tremors, because this creates sort of reverberating circuits within the striatum, and that can result in development of some repetitive movements like tremors. That's what they believe. So because tremors are due to relative excess of acetylcholine, tremors are generally not relieved that much by your dopaminergic drugs like L-dopa or dopamine receptor agonists like ropinirole and pramipexole. Instead, tremors will be relieved better with the help of anticholinergic drugs, that is central anticholinergic drugs like trihexyphenidyl. And do you have only one dopaminergic pathway in your brain? No. We have multiple other dopaminergic pathways also. For example, we have an area in the midbrain called as ventral tegmental area, VTA, which also contains dopaminergic neurons. And from the ventral tegmental area, projections are going to happen to different areas. For example, one such projection happens towards the limbic system, especially towards the nucleus accumbens. It's one of the important components of the limbic system. And this pathway is called as mesolimbic pathway. Why it's called mesolimbic? Because midbrain is mesencephalon, and because this projection happens towards the limbic system, this is called as mesolimbic pathway. And the role of dopamine in the mesolimbic pathway is thought to be reward and addiction behavior. And neurons from the ventral tegmental area also project into the cortex and multiple different areas of the cortex, especially in the temporal and the parietal lobe, where it's thought to play a role in learning and memory to some extent. So this pathway is called as mesocortical pathway. And the nomenclature can be easily understood here. And now we have discussed about three pathways of dopamine, right? So one is the nigrostrial pathway, second is the mesolimbic, and third is the mesocortical pathway. And we have another one pathway, that is tubero-infundibular pathway. So we also know that we have another important area in the midline of the brain that's called hypothalamus. In the hypothalamus, we have very important nucleus called as arcuate nucleus, which contains a type of neurons called as TIDA, that is tubero-infundibular dopaminergic neurons. And this is going to release dopamine that will be carried by the hypothalamo-hypophyseal portal system towards the anterior pituitary, where it's going to act on the lactotrophs, which contain the D2 receptors. Because D2 receptors are technically inhibitory in nature, you're going to have inhibition of the lactotrophs to release prolactin, and that's why you have reduced release of prolactin if there is more dopamine. If you're going to give a D2 receptor blocker, you're going to result in increased prolactin, as we all know. And so we have four different pathways for dopamine, important pathways that exist in the brain. One is the nigrostrial pathway, second is the mesolimbic pathway, third is the mesocortical pathway, and fourth is going to be the tubero-infundibular pathway, TIDA pathway. Now let us try and answer this question. So what does option A states? Option A states the pallidum is the source of strial input of dopamine. This is wrong. We all know the strial input of dopamine is through nigrostrial neurons from the substantia nigra pars compacta, not the pallidum. And option B states mesolimbic pathway from the ventral tegmental area to the nucleus accumbens is a glutamate pathway. That's wrong. We know that the mesolimbic pathway is a dopaminergic pathway involved in reward and addiction. Now, option C states intrinsic nuclei of the basal ganglia include the globus pallidus internal segment. That's also a wrong statement because we know the globus pallidus internus is an extrinsic segment and globus pallidus externus is an intrinsic segment. We all know that. And option D states the caudate receives input from the cortex and the substantia nigra pars compacta. This is correct. Caudate does receive input from the cortex and the substantia nigra pars compacta. Cortex is going to release glutamate at the level of striatum, and substantia nigra pars compacta is going to release dopamine at the level of striatum through nigrostrial neurons. And there are some other pathways also which are not mentioned. For example, we have thalamo-striate neurons as well. There is some feedback also that's coming from the thalamus in the form of thalamo-striate neurons that serve as an input back into the basal ganglia. We're not discussed about that. Anyways, doesn't matter. The right answer for this question is going to be option D. Simple and straightforward.